اوكي شباب، اليوم راح نكمل محاضرتنا حول البريشر بيلد اب تيست. الاسبوع السابق بدينا بحل المثال 1.5.1 اللي هو حول البريشر بيلد اب تيست، وحلينا هذا المثال باستخدام طريقة هورنر أو هورنر بلوت. حسبنا النفاذية البرمابيليتي، وعرفنا شلون نحسب السكن فاكتور when we have a pressure build up test، وأيضا عرفنا شلون نحسب الويل بور ستورج سي. هورنر بلوت مثل ما تعرفون، مثل ما أنا شرحت لكم، لازم تحسب الزمن على أساس تي بي البرودكشن تايم بلس دلتا تي divided by دلتا تي. هذا هو هورنر بلوت، والواي اكسس راح يكون اما البريشر او دلتا بي. ودلتا بي في الحاله هذه مثل ما تعرفون راح تكون البريشر at any time interval minus the pressure at the moment of the shutdown. وراح يطلع عندك الخط المستقيم اللي هو الانفينيت اكتن لاين. تحسب الميل، والميل تستخدمه في حساب النفاذيه. لحساب السكن فاكتور انت تحتاج دلتا تي 1 اور، بس هذا راح يختلف عن دلتا تي 1 اور اللي استخدمناه بالبريشر درو داون. فالحاله هذه انت لازم توجد تي بي بلس دلتا تي divided by دلتا تي. البرودكشن تايم that is given to you بلس دلتا تي اللي هو 1 ساعه مقسوم على دلتا تي اللي هو 1 ساعه. فبالمثال اللي عندكم اللي هو 1.5.1 تي بي was calculated to be 173 hours. So 173 hours plus 1 174 hours divided by 1 174 hours. راح تروح للرسم ال 174 وتصعد vertically الى ان تتقاطع مع الانفينيت اكتم لاين، وتروح تقرا قيمه الضغط. هذا هو البي دبليو اس الشتن بريشر افتر دلتا تي ايكوال تو 1 اور، وتستخدمه بمعادله السكن فاكتور تحسب قيمه السكن فاكتور. طبعا هذا الرسم مثل ما تعرفون هو السماي لوج فلوت. هسه الان حتى تحسب الويل بور ستورج، احنا الان نتكلم عن هورنر فلوت. حتى تحسب الويل بور ستورج راح تحتاج ترسم دلتا تي فيرسس دلتا بي. الان من هي دلتا تي؟ دلتا تي لازم تستخدمها دلتا تي اللي اعطيت لك، مو هورنر تايم، لا. You have to use delta t as it is delta t، وترسمها مع دلتا بي وراح يطلع عندك في بدايه عمليات الانتاج، في بدايه عمليات الغلق بهذه الحاله راح يكون عندك at early shutdown time راح يكون عندك a straight line of slope 1، ومن هذا الخط المستقيم راح تحسب تي ان دلتا بي ان وتروح للمعادله وتحسب الويل بور ستورج. الان خليني اشوفكم الحاله اللي يعني الحسابات اللي اجريت الاسبوع السابق اللي انتم كنتوا حاضرين هاي المحاضره، فراح الان اعرضها عليكم. هذا هو اللي سويناه الاسبوع السابق. هورنر بلوت رسمنا مثل ما تلاحظون تي بي بلس دلتا تي ديفايدد باي دلتا تي، وهذا هو بي دبليو اس، وحصلنا على خيط مستقيم هذا هو الانفينيت اكشن لاين، والسلوب ميل الخط المستقيم 70 استخدمناه في هذه المعادله وحسبنا النفاذيه اللي هي طلعت عندنا 31 ملي دارسي. احنا الاسبوع السابق ايضا حسبنا البرودكشن تايم. It is not given to you. It is not given to you, but you can calculate your production time if you know your cumulative production. So cumulative production is given to you. This is your cumulative production, and your flow rate also. The average flow rate is given to you. That is 385. So from the cumulative production and the average flow rate, you will be able to calculate what? To calculate the average production time. That was almost 173.3 hours. هذا زائد 1 مقسوم على 1 راح يعطيك 174.3. هذا هو اللي تستخدمه في تحديد PWS at 1 hour for skin factor calculation. What I'm saying? وحسبناه طلع بحدود 4000 مثل ما تلاحظون 4000 وقريب ال 4300. هنا اذا تلاحظوا هذه 4000 4200 هذه ال BWF 1 hour. It should be somewhere here. See, almost here. See, this is the one. وتيجي تقراها منا تقريبا 4300 almost، اقل او اكثر 4300. نعم almost 4300. وهذا استخدمناه في حساب السكن فاكتور باستخدام هذه المعادله. اوكي، الان نريد نحسب the average reservoir pressure من البلد تيست. One of the main objectives of pressure build-up test is to calculate average reservoir pressure or initial reservoir pressure. either or. إذا كان عندك المكمن جديد ما مستنزف، ما عندك آبار منتجة كثيرة، الضغط اللي راح تحسبه من البريشر بالباب تيست هو initial reservoir pressure. بس إذا كان عندك المكمن مستنزف لفترة طويلة وبآبار كثيرة، إذا بهالحالة هذه البريشر اللي تحسبه من البلداب تيست راح يكون هو average reservoir pressure. عموما ايش قد احنا ممكن نثق بالقيمه اللي راح نحسبها من البريشر بالباب تيست، وهل هي فعلا initial reservoir pressure or average reservoir pressure؟ we don't know. ولذلك احنا نفضل نسمي هذه القيمه بي ستار. شنو هي البي ستار؟ احنا ما نعرف، لكن احنا نعرف متاكدين من شغله واحده، انه هي قيمه اقل من initial reservoir pressure، اعلى من average reservoir pressure، بيناتهم. هذه هي القيمه اللي راح تطلع لنا من الرسمه، ونسميها هي عاده نسميها بي ستار. الان هذه القيمه بي ستار من وين نحصلها؟ هذه نحصلها لما نغلق البئر لفتره زمنيه طويله. الفتره الزمنيه الطويله ايش قد؟ نفترض انه انفينيتي. المنطق يقول انه اذا اغلق البئر فتره طويله الضغط راح يزداد ويستمر في الزياده. هسه هذا راح يوصل للانشال ريزرفوار بريشر، راح يوصل افريج ريزرفوار بريشر، كود بي، لكن هذا يحتاج الى زمن طويل. وعليه الثيوري بهالحاله هذه نفترض انه الشاتن تايم gonna go to infinity, then we can use it for calculating average reservoir pressure or initial reservoir pressure. اوكي، هسه اذا الشاتن تايم goes to infinity، الان ايش قد راح ناخذ القيمه على الاكس اكسس اللي هو التايم اكسس، نفس الشيء راح نقول تي بي بلس دلتا تي ديفايدد باي دلتا تي. الان تي بي بلس دلتا تي is infinity. تي بي بلس what plus infinity. See so I'm saying هذا كله divided by what by infinity also. الان تي بي بلس infinity ايش قد راح يكون؟ اكيد راح يكون infinity divided by infinity. So infinity divided by infinity 1. See what I'm saying? So this is 1. اذا انت تروح للرسمه وتستخدم قيمه y x axis لما يكون 1. راح تجي للاكس اكسس لما يكون 1 وينها هذا؟ تشوف هنا هذه 1 وتصعد بخط عمودي الى ان يتقاطع مع الانفينيت اكتن لاين. واقرا قيمه الضغط بهالحاله هذه، اقرا قيمه الضغط. ايش قد قيمه الضغط هنا؟ بحدود 4200. احنا قريب ال 4400، قريب 4440. So P star in this case 4440 بي اس. هذا هو اللي نعتقده. اما ان يكون average reservoir pressure او ربما يكون initial reservoir pressure. So one of them. اذا هذه هي الطريقه اللي نستخدمها في حساب average reservoir pressure or initial reservoir pressure. الان راح نروح الى العامل الاخر اللي ممكن نحسبه من البيلد اب تيست اللي هو الويل بور ستورج. ومثل ما قلت لكم الويل بور ستورج بهالحاله هذه انت تحتاج الى لوج فلوت between what and what. هنا اللوج فلوت لازم يكون بين دلتا تي مو هورنر تايم، لا دلتا تي، بين دلتا تي وبين دلتا بي. شوف يعني هذا دلتا تي، هذا مو هورنر تايم، هذا هورنر تايم. لاحظ تي بي بلس دلتا تي ديفايدد باي دلتا تي، تي بي بلس دلتا تي ديفايدد باي دلتا تي. هذا هورنر تايم. لا، انت ترسم بهالحاله هذه بين دلتا تي مع دلتا بي لوج فلوت. فراح يظهر عندك هنا بدايه عمليات الغلق خط مستقيم ميله واحد. هذا الميل مالته واحد. هسه لا تشيك راح تشوف انه ميله واحد. شوف عيني ميله واحد، فتحركه اللي هنا ومن ثم تقرا تي ان ذاتس بوينت 1 تيكن بوينت 1 ودلتا بي ان تيكن لايك 100. وبعدين ممكن تحسب سي من هاي المعادله. هذا كل اللي تقدر تسويه من هورنر بلوت. انا مثل ما قلت لكم على هذا الاسبوع راح اكمل حل هذا السؤال ولكن باستخدام الابروتش الاخرى. خوش هسه شنو الابروتش الاخرى؟ اذا تذكرون الاسبوع السابق قلت لكم بالبريشر بالباب تيست التايم سكيل عندنا 3 ابروتش فور ذا تايم. واحد من عندنا هورنر بلوت يحسب الزمن على اساس كونه تي بي بلس دلتا تي ديفايدد باي دلتا تي. هذه وحده من عندنا. والخيار الثاني انه نستخدم what is called equivalent time that is delta TE. شنو هي دلتا تي اي؟ تي بي تايمز دلتا تي مقسوم على تي بي بلس دلتا تي. هذا طبعا هو الأضبط. هذا دلتا تي هو الأفضل. والابروتش الثالث اللي هو يسمى ام دي اتش ميلر دايس هيتشنسون. قالوا نستخدم دلتا تي ازوتيز وقت لما يكون تي بي قيمه صغيره قياسا الى دلتا تي. هورنر بلوت نستخدمه لما يكون تي بي كبير مرتين ضعف دلتا تي. لما يكون تي بي كبير ما نقدر نهمله لان راح يكون له تاثير على الشتن بريشر، فلازم ناخذه بنظر الاعتبار. هذا يعني النظريه اللي قدمت من قبل هورنر. يعني الارجيومنت اللي قدمها هورنر على اساس استخدام تي بي بلس دلتا تي، قال عندي تي بي لما يكون تي بي كبير احنا ما نقدر نهمل تاثيره على عمليات الغلق. وهذا صحيح. هذا صحيح. كل ما كان زمن الانتاج قبل الغلق طويل جدا لازم ناخذ تاثير عمليات الانتاج بالحاله هذه. ميلر دايس هيتشنسون قالوا اوكي احنا ما نختلف في هورنر، بس اذا كان زمن الانتاج قبل الغلق قصير جدا بذاك الوقت ما راح يكون له تاثير، وبالتالي احنا ممكن نشتغل على دلتا تي ما ناخذ بنظر الاعتبار تي بي. هذا هو الميلر دايس هيتشنسون اور ام دي اتش ابروتش. ذن اثنين اضافه للابروتش الثالث اللي انا اميل الى اكثر، اللي هو مور اكيوريت، اللي هو دلتا تي اي. شنو هي دلتا تي اي؟ دلتا تي اي هي عباره عن تي بي تايمز دلتا تي مقسوم على تي بي بلس دلتا تي. هسه راح نكمل حل نفس المثال 1 5 1 باستخدام دلتا تي اي وباستخدام ميلر دايس هيتشنسون ابروتش. خلينا نسمي هذا هنا، هذا الشيت خلينا نسميه مثلا، نعيد تسميته، نسميه رينيم هورنر بلوت، هورنر بلوت حتى تميزونه. والان انا راح اضيف شيت اخر، راح اضيف شيت اخر نفس الاكسل شيت، راح اضيف شيت اخر، شيت نمبر 2، وراح اسميه دلتا تي اي. هذا راح اسميه دي تي اي حتى تميزوه. ونفس البيانات انا راح اخذها، نفس البيانات انا ما راح يعني اغير شيء، نفس البيانات راح انقلها من هاي الصفحه للصفحه الثانيه تماما، نفس البيانات، نفس السؤال انا دا اشتغل على نفس السؤال. زين عيني، هذا انقل انا بالبيانات حتى تشوفوها. وراح ايضا انقل الضغط pressure records والtime same pressure records والtime. الان راح اخليها هنا. شوف الان هذه اذا تلاحظون شباب ايش عندي انا؟ عندي هذا هو هورنر، هذا هو زمن هورنر. خوش. هسه هذا ايش راح يتغير؟ ايش راح يصير؟ راح يصير تي بي تايمز دلتا تي مقسوم على شنو؟ مقسوم على تي بي بلس دلتا تي. شوفوا عيني سوينا احنا، خلنا شويه اكبره. زين عيني. وهذا طبعا هذا هو دلتا بي، هذا دلتا بي اللي هو واقع الحال. هو من هو دلتا بي؟ هذا خلي ارجعه هنا في الشكل. وهذا هو دلتا بي، ما بي تغيير. فاذا هذا اللي راح اعيد حسابه، اللي هو الزمن. الان راح اعيد حسابه. ايش راح اقول؟ تي بي، هذا هو التي بي، هذا كونستانت، تايمز دلتا تي، هذا دلتا تي، شوفوا عيني، مقسوم على تي بي، هذا production time again this is constant plus delta t سي. وراح اقول هذا يساوي، ومن ثم راح نمشي للاخير على الكل. وطلع عندي هذا الجدول، هذا الجدول الجديد. هسه شو ارسم؟ ارسم هذا على اساس كونه اكس اكسس، ويا من؟ ويا البريشر على اساس كونه واي اكسس. هسه تسالني ممكن نرسمه دلتا بي؟ نعم ممكن نرسمه دلتا بي، ابدا ماكو مشكله. هسه راح اجي ارسم ذني انسرت، هذه سيلكت داتا اد الان هذا الزمن مالتي اللي هو دلتا تي اي مع عيني، وهذا هو الواي اكسس اللي هو البريشر. وراح نشوف اوكي. ومثل ما تعرفون انه احنا هذا راح يكون سيماي لوج بلوت، راح اغير سيماي لوج بلوت، هذا لوغاريتمك سكيل عيني شوفون. ومجرد عمليات ترتيب راح اجي هذا يعني احاول الاكس اكسس الواي اكسس اغير مكانه. اقول له الاكس اكسس should be less than 1 let be 0.001 حتى يرجع رجع للاخير. راح عمليات مره اخرى عمليات يعني ترتيب للرسمه مو أكثر لا اكثر. راح اكبر هذا السكيل مالته، هذا تو ماتش، اسوي بولد حتى تشوفونه بوضوح. وهذا نفس الشيء الواي اكسس ايضا اسوي بولد. الان اخلي مثلا العناوين للاكسس تايتلز ذني تشوفون عيني. هذا هو شنو ايش راح يكون عندي؟ دي تي اي، هذا هو الايكويفالنت تايم. خليها هم اكبر لكم اياه، الايكويفالنت تايم. وهذا هو شنو؟ هذا هو بي دبليو اس، بي اس اي سي. هذا هم خلينا نكبره حتى تشوفوه واضحه هاي شباب. ها عيني. هسه هذني هذا الاكس اكسس والواي اكسس. الان هذا الواي اكسس انا ما اريد هذا الجو، ماكو داعي ابدا من الصفر، خلي ابدا من 3000 حتى يكون الرسم اكثر وضوح. شفت؟ الان هو يشبه الرسمه السابقه بالضبط، يشبهها. وين الجزء اللي يشتغل عليه؟ هذا هو الجزء اللي يشتغل عليه. هذا الجزء شو يمثل؟ ويل بور ستورج وسكن فاكتور، انا ما اشتغل عليه. لازم اكون بعيد عنه. فاشتغل على هذا الجزء اللي يمثل لي انفينيت اكتن لاين. نفس الشيء انا راح اقوم بنفس العمليات تماما، راح اقوم بنفس العمليات. راح اجي اشوف لي هذا الخط اللي هو الانفينيت اكتن لاين، تشوفونه يا انا عيني، هذا هو الانفينيت اكتن لاين. عيني بقى لاحظوا، خلي اكبر لكم اياه شويه حتى يكون واضح لكم. اخلي لونه احمر، وهذه الماركرز خلي اكبرها حتى تشوفوها بوضوح. عيني هذه تشوفون. اوكي I think now we are good. هسه هذا شو اطلع من عنده؟ كالمعتاد نطلع من عنده الميل اللي هو السلوب. ايش قد هسه اذا اخلي الجريدز اخليها اكثر وضوح. الجريد لاينز البرايمري والفيرتيكال. عيني الان اخلي ذن الرئيسيات واضحات شويه حتى تميزوهن عن البقيه. هذه as you can see black color، وهذا ايضا راح اخليها black. الان راح اروح الماينر جريدز، اغير اللون، اخلي هذا تشوفوه شويه الان اصبحت اكثر وضوح. وهذه ايضا مره اخرى احاول اخليها اكثر وضوح. الان اذا اجي هذه 4200، اذا اجي احسب السلوب 4240 280 320 360. اذا عندي اني 4360 ناقص البريشر ات 1، سو 4240 280 تقريبا 290. 4290 ايش قد عندي؟ طلع عندي 70. اذا ترجع الهورنر بلوت تشوفون الميل ايش قد بهورنر بلوت، ايضا 70. ماكو مشكله. اذا الان انا ايضا طلعت 70 بهالحاله هذه. خلي اكبر هذه حتى تشوفوها بوضوح. فاذا عندي طلع الان الميل 70. هسه اجي احسب النفاذيه. البيرمابيلتي should be calculated using the same model اللي احنا انتم تعرفوا الموديل للنفاذيه. من هو هذا موديل للنفاذيه؟ هذا الموديل للنفاذيه شباب. اذا كي الان كي شو تساوي لنا؟ كي تساوي لنا 162.6 تايمز وات؟ كيو نيو بي. كيو نيو الفيسكوزيتي. where is that? there is mu oil formation volume factor divided by what? Slope times what? H formation thickness. same. ما احنا حسبناها بهورنر بلوت ايضا 31 ملي دارسي. هاشام طلعت عندنا 31 ملي دارسي نفس الشيء. الان اجي احسب السكن فاكتور. هنا السكن فاكتور انت تحتاج قيمه الضغط لما دلتا تي 1 اور، بس انت ما عندك دلتا تي 1 اور. عندك تي بي تايمز دلتا تي مقسوم على تي بي بلس دلتا تي. فلازم تطلع شو تقول تي بي بلس دلتا تي. ايش قد دلتا تي؟ سوري تايمز دلتا تي اللي هي ايش قد؟ 1 مقسوم على تي بي بلس وات؟ بلس 1. سي هذا ايش قد يساوي؟ هسه نشوف هذا المقدار ايش قد يساوي واقع الحال. تي بي اللي هي 173، فهذه هي عباره عن شنو؟ 173 هذا هو برودكشن تايم تايمز 1 مقسوم على برودكشن تايم بلس 1. ذاتس اول. اذا راح يكون عندك واحد almost 1. 173 في واحد 173 مقسوم على 174 قريب الواحد. فاذا ايش راح تسوي انت الان؟ راح تيجي ترسم خط من الواحد وتصعد نحو الاعلى. هذا شو ينطيك البي دبليو اس shut-in pressure after 1 hour. How much? Could you please read it? If you read it now, you're going to find that is so BWS 1 hour. In this case, how much? 4280. 4280 PSI. 4280 PSI. الآن أصبح بإمكانك تحسب السكن فاكتور. تستخدم هذا الموديل، إذا أكيد تعرفوه، موديل خاص بالسكن فاكتور اللي هو هذا. عيني هذا تشوفونه. فأجي الآن أحسب السكن فاكتور اس اللي هي شو تساوي لنا؟ 1.151 times what? Times BWS 1 hour, this one, minus PWS at the moment of the shutting. Where is that? Here is the one at the moment of the shutting. See? مقسوم على شنو؟ على السلوب اللي هو 70 minus log K هذه K permeability divided by what? Phi mu CT RW square, phi mu CT, phi porosity, mu viscosity, CT RW square. Where is that? RW, I cannot see RW. Well, yes, RW square. Close the parenthesis plus 3.3.23. Close the parenthesis again. And this would be your skin factor. Okay, let me check it. Okay, okay. So 1.51, there is no 8. Okay, times this one, log minus log. Good, good, good. Okay, there is nothing wrong. So skin factor is 5.6. Let us see skin factor calculated by Horner. It is 6.3. 6.3, as the pressure here is calculated as 4,300, while for our case it is 4,280. So this is your skin factor. Now we need to calculate what? We need to calculate, again, we need to calculate B star, or initial reservoir pressure, or average reservoir pressure. Again, the same idea that initial reservoir pressure or average reservoir pressure, we could reach them when the shutting time gonna go to infinity. So delta T gonna go to what? Gonna go to infinity. Now TB times infinity, infinity, divided by TB plus infinity, infinity. So infinity divided by infinity 1. In this case, we're gonna move with what? We're gonna move with the same line. So let me put it here. Here is TP times DT divided by TP plus DT. Okay. So TB in this case 173 times DT gonna go to infinity. This would be what? Infinity. Divided by TB 173 divide plus infinity, infinity. So infinity divided by infinity 1. Therefore, B star in this case will be the same for the shut-in time after 1 hour. Shut-in time after 1 hour. Here is the one that we need to look for it. So it is almost 4280 BSI. Okay. Now we need to calculate well-bore storage. Now well-bore storage will be the same for Horner plot. We are not going to change. What we are going to do, we are going to use delta T and delta B. This is the one that we need to look for it. Let me remove this one here. And we are going to change this one from delta TE, we will use delta T. And instead of a pressure, we are going to use what? We're going to use delta pressure. And this one going to be from 0, as you can see. We will get it from 0. And this should be changed to what? This should be changed to log plot. So both of them will be log. See, now this is the well-bore storage. This is 1. Let me have it 1 exactly. This is 1, and we are going to move it here, and we will have Tn. Tn, how much Tn in this case? 0.1. Same. How much dBn? dBWSN? Almost 100. Same. See? Same. Same for Horner. Nothing has been changed in this case. And we're going to bring this one, this model, see? And we're going to put it here. So C in this case will be what? C will be QB. This is a Q. Oil formation volume factor, where is that? The QB divided by 24 times Tn. Here is Tn divided by delta Tn, and this is your CP. This is parallel per PSI. This is your the unit for the well water storage. Okay. Same as you can see, same to Horner plot. Same to Horner plot. Exactly. So this is delta TE. Here's what we need to do for delta TE. Now, the initial reservoir pressure calculated by delta TE is not accurate like the one calculated by Horner plot. Okay. So now what we need to do? Now we need to do the same using what? Using Miller-Dice-Hutchinson. So I am going to create a new sheet, and I'm going to rename this sheet. I will call it MDH. Now MDH said that we can use delta T as delta T. Delta T as delta T. So let me bring the data with me to sheet number 3. See, this is sheet number 3. Okay. And let me bring the pressure records with me. This is the pressure records here. Okay. And going to page number 3. See. And now what we need. So see, this is delta T. So we do not need. This column is not necessary. See. So we're going to remove this one. We do not need it because basically we have delta T, and we're going to use delta T as it is delta T. And this one will be what? This one will be, I'm going to put it here. See? So this is your delta T, this is your pressure. Now we are gonna plot. This is by Miller-Dice-Hutchinson. Select data, add, and delta T. With what? With your pressure. Again, this should be semi-log plot. See, guys? And now we need, there is no need to start from 0. So we could start from 3000. See? You can see that the shape of the pressure curve, the shape here, similar to the shape obtained by Horner plot and delta TE. Yes, and let me make it clear. Remove this one, make the markers more clear. Here is built-in. Okay. Now let me change those. Oh, actually, would be better on this. Okay, good. And let me add the titles. So x-axis, this would be what? Delta T. See? Delta T. And this one what? BWS. BSI. Of course, delta T, this would be what? Delta T hours, of course. Hours. See? Now let me add the grid lines, minor grid lines, and I'm gonna make them clear. So This would be clear. This would be clear. The minors also. I think now they are clear, guys. Okay. So this is your infinite octane line. This is your infinite octane line. So now we're gonna have the straight line of infinite octane line. This is the one that we are looking for. See? Okay. Now doing the same, we will look for the slope n and see how much n. So m in this case, I'm gonna look for m. So here it is not clear. Oh, I don't know why I lost grid lines. So let me make them clear. Now 4 to 40, 4 to 80, 320, 360. So 4360 minus 400 to 40, 80 again. 4290. So it's a 70 again. We got the same. We got the same. Now we're going to calculate the permeability doing the same. So here is the permeability. Let me bring the permeability model here. So the permeability is what will be, of course, will be the same. That is 331 actually times this is a Q mu. This is a mu oil formation volume factor, and this is your slope times formation thickness, and this is your permeability, millidarcy. See? Now we're going to calculate BWS. BWS 1 hour. In this case, delta T 1 hour, delta T 1 hour. You do not need to do it. Just delta T 1 hour and get, so DT 1 hour. See, guys? DT 1 hour. Okay? And then calculate BWS at delta T 1 hour. BWS 1 hour. See? هسه راح نجي مثل ما تلاحظون شباب، هذا الواحد شوف 4280 ايضا بي اس اي. سي وات ام سين؟ سيم. خلي هذا اوضح لكم اياه. يعني I think it could be a little bit more than, so close to 300. Okay, yes, it is close to 300 actually. Okay. Now we can calculate skin factor. Here is the model for skin factor. So S is 1.151 times BWS 1 hour minus BWS at the moment of the shut-in divided by skin factor slope minus log K divided by phi mu CTRW square, phi mu CT RW square, close and close, plus 3.23 close, and this is your skin factor 6.34. Now how can we estimate initial reservoir pressure, initial or average reservoir pressure from MDH. As I told you, initial reservoir pressure, average reservoir pressure can be estimated when delta T, when the shutting time gonna go to infinity. And for this case, we do not have the infinity. And there is no way to use this one to calculate initial reservoir pressure or initial or average reservoir pressure. But what we can do, we can, for example, estimate the pressure after 1,000 or 10,000 hours. So what we can do actually, we can change this one and say, okay, and instead of, so we're gonna put it like this, see? So now this is 10,000 hours. So 10,000 hours. So it means that how many years we do have? 10,000 hours divided by 24. This is days. Okay? And this one gonna give you what? This one divided by 365. This one gonna give you years. So after 1 year, we could calculate the pressure. You could say, okay, 1 year is really small. You can increase this one, put it 100,000 and increase your scale here to, see, and you can get the pressure. See, the extrapolation of the this is 100,000, 11 years. We're gonna shut in the well 11. This is not logic, but let me say we're gonna shut in the well. And you can read the pressure here. So it is almost 440, 444, 448, 450, 4,520 psi. Here is the way how to calculate initial reservoir pressure or average reservoir. This is kind of approximated approach. It's not like Horner plot. Horner plot, when you have infinite shutting time, then Tp plus delta T divided by delta T gonna be 1. Then you can go to 1 and read the pressure. No, it's not like this. But you can assume we're gonna shut in the well for a long time. How much this long time? It depends. If you can say, okay, 10,000 hours, 100,000 hours. Otherwise, you cannot estimate average or initial reservoir pressure. Now, for well bore storage, it will be kind of redundant. We're going to use the same concept used by Horner, the same concept used at delta TE, and here we can use, again, guys, put it here, okay, and we do not need to go for all of that. So let me remove some of the points here, okay, and now we're going to say this one should be what should be log, see, and here is what we have. Let me change the x-axis from 0. To delta V. This is delta V. And we are going to move to 0. We do not need to start from 3000. See? Okay. And here is delta V instead of pressure. So this one, we should say starting from 0. See, now this should be log scale, as you know. This should be log scale. So it is similar to what we have before. Then we're gonna look for the straight line of slope 1. So this is the straight line of slope 1, and we're gonna move it here. So it will be the same, almost the same things that we have them before. So Tn, here is Tn.1, and we're gonna move, and as you can see, there will be 100. So Tn, in this case, Tn will be 0.1, and dBWSN, this would be 100, and then we're gonna calculate C. So C is calculated using this model. Will be the same, of course, QB, Q, oil formation volume factor divided by 24 times Tn divided by delta Vn, and this is your C. This is parallel per PSI. So here is the analysis, pressure analysis, using Horner plot, using delta TE, and of course Miller Dice Hutchinson. I hope you will understand the explanations for the three cases. If there is something wrong, if you think that you are lost, you couldn't understand me, you couldn't catch me, you can contact me. So I'm going to save this one. Okay, let me save it. Okay, we cannot reach. Okay, okay, this will be fine. Okay, pounds. Okay, okay, yes, yes, replace. Okay, I'm going to post example 151 using the Telegram, so you could use it later. Okay, so let me stop sharing now, and let me continue talking about the rest of the topic. Okay, uh, I don't know how much time we still have before the disconnection, but I guess okay. So now we have 7:40. Okay. Okay, let me continue talking about this one. Share. Oh, where is that? Why we do not have it? Okay. Chat. So this is the notes that we need to cover them. So let me see, where is 151. We need to go all the way to 151. No, this is 162. Okay, here is 151. So this is 151. Let me see. Yes, mega dissection. Okay, equivalent time. Okay. Yeah, this is 151. So right now I'm done with 151. You just need to read section 2 of 151. This is the derivative techniques. You do not need to consider it. It's not required. Now we're going to go to how can we calculate the distance to the boundaries. One of the important function for well test analysis is to calculate the distance between the producing wells and the reservoir boundary. It's not only reservoir boundary actually. For example, if we have natural fault close to the producing well bores, we can estimate the distance to the fault using the well test analysis. هذه العملية عملية حساب المسافة لحدود المكمن، أو if we have faults تتطلب استخدام ما يعرف بالsuperposition theory. Superposition in space, not in time. Okay, the superposition theory does have two conditions: space and time. Space and time. Now, superposition in time, what does it mean, superposition in time? Superposition in time states that the production at different times could have an impact on the pressure behavior. And this is true. While the superposition in space says that the production from a wellbore located at a distance from another well, there should be some impact on the pressure behavior of the neighbors caused by the production from the producing well. So when we have two producing wells, one here and one there, when we start the production from this well, there will be some impact on the pressure behavior of that well. And the impact of the production rate at this well on the pressure at that well depends on the distance between these two wells. This is called the superposition in space. The theory itself suggested that the impact on the neighbors could be described by an imaginary well. So what does it mean, an imaginary well? We can say, okay, this is your producing well. This is your producing well. See, this is your producing well. And you're going to produce by Q. This is real well, producing well Q. And let me say that we have reservoir boundary here, or fault here. This is reservoir boundary or fault. Now, the impact of the reservoir boundary on the producing well could be described by an imaginary well located at the same distance, but in the other side of the reservoir boundary. So as we could have imaginary well here, This is not real. This is imaginary well here. At the same distance, so if this is R, this should be also R. If this one is going to produce Q, this one should produce also by Q. But again, this is not real well. This is an imaginary well. So the pressure drop here, delta B here, delta B here, delta B here is caused by the production from the well itself, the production from the well itself, and the production from an imaginary well located at the same distance between the producing wellbore and the reservoir boundary, but in the other direction. See? So in this case, delta B total would be what? Would be delta B1 plus delta B2. Delta B1 is the pressure drop caused by the production from the wellbore itself, while delta B2 is the pressure drop caused by as if we have another producing well located at some distance beyond the reservoir boundary. See? So this is what, see? This part, see? And here's the second part. So this is delta B1, see? And this is delta B2. So delta B1 depends on what? Depends on the wellbore radius. How much R sub P? Because we have the production from this wellbore. So the pressure in this case is calculated at the wellbore. So R in this case will be wellbore radius. But when we need to calculate delta B caused by the imaginary well, we have to consider the distance from the real well and the imaginary well. So this would be kind of R sub C square. And this would be really very long distance. It's not small distance. And it has the power of 2. So this would be really very big number. So this number divided by very big number will be really very small. So ln for very small number will be really very small. Or it could be what? Could be negative plus this one. So what I need to say that this number could be really non-significant, especially if the distance is really long. But if the distance is really short, this would be really significant. So we have to consider it. So if we have reservoir boundary, if we have fault, then the pressure drop caused by the pressure drop at the well pore or at the producing well pore comes from 2 pressure drops. One of them, the pressure drop caused by the production from the wellbore itself. And the second one, the pressure drop from an imaginary well located at some distance from the reservoir boundary or the fault. And the second pressure drop may be significant, may not be significant, depending on what? Depending on the distance between the real wellbore and the reservoir boundary, because we are going to put 2 times the distance to the reservoir boundary. This is the superposition in space. Okay, now let me ask you, let us make it more complicated. How about if we have, this is your producing well, this is your producing well, see? This is your producing well, and this is your reservoir boundary. So in this case, we're going to put another well, imaginary well here. And we're going to calculate delta B as delta B1 plus delta B2. Okay, how about if we have 2 boundaries like this? Again, superposition theory in space says that we have to put another well here. See, okay. We're going to put one here. So delta B in this case will be delta B1 plus delta B2 comes from what? From this one, and delta B3. See what I'm saying? Delta B3 comes from that one. Okay. So how about if we have another one here? Easy to do. We're going to put another well here. So we're going to put delta B4. See? Delta B4 comes from what? Comes from this one. And if we have closed reservoir, then we have to put another well here. And we're going to increase to delta B5. See what I'm saying? Here is superposition in space. This is the theory of superposition in space. Okay? You can imagine that the impact of reservoir boundary as if we have producing well at some distance beyond the boundary. And the imaginary wells could have an impact on the pressure behavior of the producing well. This is what is called superposition theory. Now, how can we use this theory for calculating the distance? Now, it has been found that when we have single reservoir boundary, or when we have a fault close to the producing well, the slope, we will have two infinite actin lines, not one. We will have two infinite actin lines. When you plot semi-log T versus delta B, there will be two infinite actin lines. The slope of the second is double time the slope of the first. When you have two infinite actin lines, so you have to say, okay, we are close to the reservoir boundary, or one of the reservoir boundary, or we are close to the fault. When the pressure behavior gonna give you two infinite actin line, and the slope of the second infinite actin line is twice the value of the slope of the first infinite actin line, then you have to think about either you are close to one of the reservoir boundary, or you are close to the fault. If you look carefully at this plot here, see, this is for pressure and T, time, not delta V and T. So as you can see, we have two infinite actin lines. So this is two infinite actin line here. See, this is the first one, and this is the second one. This is the pressure, not delta V, and here is time. So in this case, what we have, let me make it bigger so you could understand this one. Okay, this one is good. See, so when you have something like that, see, two infinite actin lines. See, this is the first infinite actin line. See, here is the first infinite actin line, and this is the second infinite actin line. The slope of this one is double the value, twice the value of the slope of that one. So the slope here 15.4, where the slope here is 31. So it is double. When you have something like that, then you have to think either you are close to one of the reservoir boundary, or you are close to a fault. Now, the intersection point between the two lines, the two infinite actin line, here's the intersection point, okay? This is called Tx, the intersection point between the two straight lines. This would give you Tx. Tx is used to calculate the distance to the reservoir boundary or to the fault if we have a fault. So D, the distance, is calculated by what? By this model. So K, the permeability. Be careful. K is calculated from the slope of the first infinite actin line. K, again, let me repeat this one because this is important. Most of you could make a mistake. K is calculated from the slope of the first infinite actin line, not from the slope of the second infinite actin line. No. K is calculated from the slope of the first infinite actin line. Let me repeat it. K is calculated from the slope of the first infinite actin line. Then you have to get Tx and put Tx here. Then phi mu ct will be given to you. Then you will be able to calculate D. Now, skin factor is calculated from where? Skin factor is calculated from T1 hour, but it is taken from the infinite actin line, not from the second infinite actin line, from the first infinite actin line. K and the skin factor, both of them are calculated from the first infinite actin line, not from the second infinite actin line. See what I'm saying? Okay. I think we have an example. Yes, here is an example. So we're going to solve this one. This is example 161. Let me see. I think I do have this one. So let me see. This is okay. Fire. Yeah, here is 161. Okay. Okay. I think we are good now. Let me share it with you. 161. Where is that? 161. Yeah, here's 161. I hope. Okay. Now this is 161. Okay. So here is 161. 161. Okay. Let me make it clear. Okay. Good, 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 good. Okay, good, good. And let me remove all of that so we could start from the beginning. Let me remove this one. Let me remove the float. And this is our pressure behavior given to us. Okay. Okay. Good. So here's what we have. Here is what we have. Okay. Okay. Now we're gonna start as usual. We're gonna start with delta D, for example, dPWF. This would be what? This would be average reservoir pressure, this one, see, minus the pressure at the time intervals given to you. And you are going to move down, see, and this would be what? This would be, okay. Okay, so this is your dBWF, and you're going to go with semi-log plot of what? Semi-log plot of T. This is drawdown. So we're going to go with add your time, production time, all the way to the last reading, and delta V. See delta V. So this is your plot. Now, as I know, this should be semi-log plot. So log for this one, and let me make it clear. So we do have some of the things that we need to do then. Let me make it okay. There is. Okay. Now let me get the y-axis to the right place. Put it in the right place. Okay. Okay. Good. Now what else? Let me put the titles for the axis. The axis titles. Okay. So this is T hours. See guys. Okay. And let me make it bigger. And here is what? Here is DPWF. This is PSI. And let me make it bigger. See? And here, this is your pressure. Let me make them clear. Okay. Now let us see what we have. It is clear that we could have two infinite actor line. So here is the first. See? Let me make it bigger. So this is the first one. And as you can see, there is another one here. Okay, see guys, there is another one here. Say, let me make them clear. This would be red color, and this would be also red color. Okay. So when you have something like that, you have to think about what? Either you are close to one of the reservoir boundary, or you are close to a fault. Now, before going to calculate D, you need to calculate K, skin factor, and the other thing. So what you need to calculate the slope of what? The slope of the first infinite actor line. Which one is the first infinite actor line? The one comes early. The one comes early is this one, not that one, because this is the time. So this one comes early. So what would be the slope in this case? This is 1. Let me add the grid lines so you could see that clear. This is the grid lines, okay. No, not this one. No, I need to put like this. And and I need to also change those to good. So now I need to read the slope in this case. The slope is what? So for 1, it is 8, 80, 84, 88. Minus, this is from 1.1, 60, 64, 68, 72. So it is 16. This is M1, the first infinite actor line. Let me check M2. Let me check M2. M2 from 100, so 120, 24, 28, 132, 136. 136 minus from 10, 104, 108. See, 28, while this one is 16. So I think this would be, we need to just a little bit shift here, okay. So I think this should be, in this case, 180, 84, 88, actually 89. See, 89. And this one is 60, 648, almost 70, 74. Let me get back to 88. Okay. So it's kind of 14 and 28. Let me say something like that. 14 and 28. They have to be double, actually. They have to be double. They have to be double. This is the what the superposition theory says. Okay. Now, if you need to calculate K, you have to think about the first infinite octant line. So this is the one that you have to use. And we know that the permeability is calculated by what? You know, guys, the permeability. Let me bring the model for the permeability. So here is the models for the permeability, skin factor, and the distance. So the permeability is 162.6 times Q. We need to put the Q. This is the Q. Here is the Q. Q mu oil formation volume factor divided by what? Slope first infinite octant line times what? H, formation thickness. Close. So this is your permeability. It is millidarcy. See what I'm saying? Now we need to calculate skin factor. In this case, you have to get what? You have to get T1 hour. See, T1 hour. And get the pressure. Get dBWF 1 hour. See? dBWF 1 hour. This would be what? This would be, again, you be careful. You have to work with the first infinite octant line. So this is first infinite octant line. Go to this one and read delta B. How much delta B? 88. 88. Almost 88. So skin factor in this case will be what? Skin factor will be 1.151 times. This is BI minus B1 hour. It is 88. So it is 88 minus your slope for the first infinite octant line minus log K, this is K, divided by phi mu CT, phi mu CT RW square, close, plus 3.23, close. So this is your skin factor. So now you are done. Now you are done. Now we need to calculate D. For D, what you need to get the Tx, the intersection point between the two infinite octant lines. So where is that? This is your Tx, see? This is your Tx, see? Here is the intersection point. So this is your Tx. So you're gonna move down and read Tx. How much Tx? 1, 2, 3, 4, 5, 6, almost 6. So Tx is 6 hours. Then you will be able to calculate D, the distance, as 0.01217 times square root of what? K, this is K, times Tx, this is your Tx. Sorry, let me get back. This should be plus this square root of K, this is K, times Tx, this is Tx, divided by phi mu Ct, phi porosity, mu Ct, close, and get this is fit. So the distance between the producing well and one of the reservoir boundary or could be fault, 395 feet. 395 feet. Okay. Now we can calculate, of course, wellbore storage. There will be no problem. We can calculate the wellbore storage for this equation. So what we need in this case, we need to calculate delta B, and we do have delta B. So this is log float. Now we have to put this one log also. So this should be logarithmic, see? And again, what we have, this is the first part. Here is the first part. So what we need a unit slope line this is our unit slope line. So this is the slope of 1, as you can see, and then you're gonna move here. So this is your line. See, you are here. Okay. Now you can get any value, for example, 0.01, and move to the line and read. So Tn in this case, what is Tn in this case? Tn in this case is 0.001, and you're going to calculate dBWFN. This would be what? This would be almost 70. And then you are going to calculate C. C is what? C, you know, guys, C is what? Let me bring C to you. So C is what? C is no, this one actually. We need another one. Okay. No, this one. Okay. Yeah, here is C. Here is C. Okay. So this is C, and C is what? Q times B, Q times B divided by 24 times what? Tn divided by delta BWF, and this is your parallel per PSI. This is C. Okay. So we got everything now, and we are done. Okay. I hope this is clear also. So I am going to save it to you so you could use it. I will put it in the Telegram so you could get back to this example when you will need it. Okay, good. Okay. Now let me get back to share with you the rest of the topic. Okay. This is 151. Okay, done. We are done with this one. Okay, and here it is. 161. We are done with 161. Okay. Now we did it. I mean, we have calculated the distance to the boundary or to the fault if we have pressure drawdown test. Now, if we have a pressure build-up test, we're going to do the same, but we're going to follow Horner plot. So for pressure build-up test, we will follow Horner plot, as you can see. So we are going to have TB plus delta T divided by delta T versus BWS. Then you will have the two infinite action lines. And there should be the slope of the second infinite action line double the value of the slope of the first infinite action line. You will be able also to calculate the permeability from the first infinite action line, the slope of the first infinite action line. And then you will be able to calculate the skin factor from the first infinite action line. While D is taken from what? D is taken from the intersection point between the two lines. It is similar. These are the models. These are the models in case if we have pressure build-up test using Horner plot. This is for BWS. But if you're going to work with delta D, you're going to use what? Miller-Dice-Hutchinson. Miller-Dice-Hutchinson, you're going to plot delta T as it is, delta T, with delta D. In this case, D, you're going to use delta Tx. Okay? So it doesn't matter if you have TB plus delta T divided by delta T, or delta TE, or delta T. You're going to have Tx. You are going to use the value of Tx. The value of Tx will be taken from where? From the intersection point of the two lines. So if you use Horner plot, if you use Miller-Dice-Hutchinson, if you use delta TE, there will be two infinite action line, and the intersection point of the straight lines come from these two infinite action line, they're going to give you what? They're going to give you Tx, and you're going to put it in the main model for the distance calculation. See? So, for example, for Horner plot, you're going to put, see, TB divided by Tx. This is Tx. For delta TE, you're going to use delta TE as it is. For MDH, you're going to use delta TX. Okay? And example 162 illustrates the application for calculating the distance to the boundary or to the fault if you have a pressure build-up test. Let me see if I have this one in my database so we could use it directly. Otherwise, we will work together solving example 162. There is no 162, so what I am going to do, I'm going to have the data for 162. Okay, here is the data. Okay, you just need to follow me, guys. So this is the data that we need to use. Okay, and now I'm going to open Excel sheet. This is the Excel sheet that we need. See, guys. Okay, and this is the data here, and I will share this one with you. So where is that? Okay. Okay. 162 actually. Okay. Now I am going to share 162 with you, so you could follow me. Okay. I think we are ready now. Where is 16? Here is 162. So this is the data for 162 given to us. So what we have RW, that is 5 inch, or this would be what? 5 divided by 12. This would be fit. So you have to be careful. See, this is RW, and here is CT. How much CT? 0.00022. This is PSI minus 1. Good. And we have also what? Initial reservoir pressure given to us. That is a 3750 PSI. Good. What else? We have also the flow rate given to us like 180 STP per day. Good. And we have also porosity given to us like what? Like 0.14. Good. And also we have known the thickness, 18 feet. We know also the viscosity, that is 1.8 centipoise. We know also the density, which is not important actually. Density. This would be 56.8 pound per cubic feet. Okay. And we have the cumulative production. This is important to calculate the average production time. That is 9,000 STP. And what else? We have oil formation volume factor. This is 131. So here is the reservoir and the fluid properties given to us. And let me make all of them. Let me make the font bigger. Okay. So what we need, let me remove this one like this. Okay. So here's what we have, guys. Okay. Now what else we have? delta T, this is hours, and of course the PWS, the shut-in pressure, PSI, because this is build-up test. So the time starting from 0, 1.1, 1.6, 2.5, 3.5, 5, 7, 9, 13, 20, 30, 40, 50, 70, 100, 150, and 250. Here is the time interval. Now we're going to read 2840, 3170, 3199, 3240, 3278, 3290, 3302, 3310, 3320, 3333, and 3343, 3350, 3363, 3382, 3400, 3423, and finally 3450. So I'm going to remove this one. I don't need it. So this is your uh, pressure records with time. Now we're going to go with Horner plot. So what we need TP plus dt divided by dt. This is Horner plot. Now, do we have TB? No, we do not have TB, but we can calculate TB. What is TB? TB is cumulative production, as you know, guys, divided by what? By Q. And this would be what? 50 days. See? But we do not need it in days. We need it in hours. So we have to change this one. 50 times 24. This would be hours. So this is your production time. Therefore, for this one, you're going to say, okay, this is TP constant plus delta T divided by delta T. And you're going to do it for all. See, guys? Now we are going to plot this one. Insert. See, guys? I'm going to remove this one. Select data. Add. So Horner time versus pressure. See? Good. Okay. So this should be log scale, as you know, guys. So this should be log scale. See? Now we're going to follow the same things. Make them clear. Okay, make them clear, guys. Okay. Okay. And you can add the titles. This would be what? TB plus DT divided by DT. And and this would be what? BWS PSI. Make it also clear. Okay, good. So here's what we have. Now I can change the markers if you would like. Okay, now it's clear that we have two infinite octane line. This is infinite octane line here. See, this is infinite octane line. Let me do it like this. So this is infinite octane line. So red color. Okay, and here is the second infinite octane line. This is the second. See, guys, this is the second infinite octane line. Here is the one, as you can see here. Okay. Now we need to see the slope of the, okay. In this case, this one is the first infinite actor line again, not that one, because this one gonna come early. This is the small time. The bigger value for the time axis, the early time is. So the slope in this case would be what? Let me add, of course, let me change the grid lines here. Black. And those should be also black. And now I am going to add the minor grids. Horizontally also, we are going to do the same. Okay. So I am going to look for M1. So M1 here is 110. So we are between what? Between 335, 3035, 36, 37, 38, 38, 3385 minus what? 100. 3,300, 10, 15. 3, 3, 15. So this is almost 70. Of course, M2 should be double the value. So how much? This one, 3, 3, so 3, 3, 5, 5 minus 315, 316, 317, 318. See, 175. So 70, 175. So this is more than twice. So we need to look at it again. Okay. So let me see. This one should be a little bit up, and this should be like this. And we are gonna recalculate this one. So it is 3, 3, 5, 6, 7, 8, 9. See, 9. And how about this one? 3, 3, 3, 3,300, 10, almost 15. So how much we have? It should be more. 3, 3, 75. Let me look at this one and see if there is something that we can do here. So 3, 3, 5, 5, 3, 3, 5, 5, yes. Okay. And 3175, 3180, good, 3180. This would be still more. So let me see. So this would be 3, 4, 3, 2 actually, 3295. So is it a 329? No, 3, 3. Sorry, 3, 3, 3, 3, 300, 3, 10, 3, 3, 40, 45 actually, 3, 3, 45. So we are close now, 75 and 165. Now we may need to change a little bit that one again, make it a little bit bigger. I think we are good now. So we are close to, let me see, 95. Okay. Yes, now we can accept that. Okay, 18 and 165, something like that. So this is your slope. This is the one that you need to work with. Now you have to calculate what? You have to calculate the permeability in this case. So for Horner plot, here is the models that you need to use them. See, here is the models should be used for Horner. So K is what? K is 162.6 times Q times mu. Where is the viscosity? Let me see. Where is that? Mu times oil formation volume factor divided by slope for the first line times formation thickness. So this is your permeability millidarcy. Now you need to calculate skin factor. In this case, you need to get BWS after 1 hour. In this case, what you are going to do, TB plus 1 divided by 1. See? And this would be what? This would be 1,200 plus 1, see, divided by 1. So it is 1 to 1,000. This is 1,000. See, this is 1,000. And this is 2,000. So you are here. You are here. And now you are going to move up and read the pressure. So it is almost what? It is almost 3 to 40. 3. So BWS 1 hour. This would be 3240 psi. Taken from where? Taken from the first infinite action line. First infinite action line. Then you can calculate skin factor. That is 1.151 times what? Times this pressure, see, minus the pressure at the moment of the shut-in. See, this one, closed, divided by the slope. Slope of what? First infinite action line. Minus log K, this is K, divided by what? Phi mu CT, phi mu CT RW square, close plus 3.23 and close, and you will get the skin factor. So you got the skin factor. Now we need to calculate TX. So please get TX as it is from the intersection point of the two lines. So this is your TX, see? How much TX now, in this case? TX is what? Is 200, see? 200. Now, D is what? D is 0.01217 times square root of what? Of K. This is your K. Times your production time. This is your production time, see? Divided by what? Divided by phi. This is your porosity. Mu CT times TX. This is TX. See? This is your TX. See? Close. And this is your distance. Fit. So you are very close. You are very close to the pounder in this case. Okay. And the permeability has been found in the slides 58, where the distance 172. This is because of TX is taken 35, while our TX is, this is 100, okay. So, sorry guys, so I made a mistake. Actually, this is wellbore storage. So this is your second line. Yeah, this is your second line. I thought there is something wrong. Okay, sorry for that. I'm going to repeat everything. This is your second line, not that one, because this one for the. So this is your TX. Okay, this is your TX. Okay, so let me check. Okay, the slope in this case is what? See, yes, same. 3420. So 3420 minus 3260 70 3280. Yes, and this one get back to 40. That's what we have started with. Okay. Okay. The 3, 60, 70, 80, 90, 95 minus 315. 3315. Okay. And this should be what? Okay. Let me see. 3, 4, 15. 3, 4, 15. 3, 4, 15. Is it this? 3, 4, 15 minus 3, 2, 70. 70. Okay, we have to increase this one or decrease this one actually. Something like that. So this would be what? 3390. Okay. Yeah, something like this would be accepted. No, now we are good. So this is the permeability. Okay. And for P1 hour, we need to recalculate P1 hour. So P1 hour here, so 3240. It's calculated 1,200. Yes, okay. So 324, good. And this is TX. We need to change TX. Now we have 10, 20, almost 28. So this is our distance. So if for the mistake, this should be for the well bore storage, because the big the bigger number for Horner plot, the early time is the bigger number for Horner plot, the early time is, and we would not like to use the early time. So this is your first infinite Acton line, and this is your second infinite Acton line. Now here is how it works with the pressure build-up test. Now we can do the same using delta TE or using Miller-Dice-Hutchinson. Now let me repeat this one using Miller-Dice-Hutchinson. So let me rename this one and saying that this is Horner, see? And now I am going to add another one. I'm going to call it MDH. This is MDH, and we will see MDH. See, let me copy the same things here. Okay, okay, good. And now I'm going to copy also the pressure records. See, guys. Now for Miller-Dice-Hutchinson, we're gonna work with what? We're gonna work with delta T as it is. I mean, we do not need to use TB plus delta T divided by delta T, or delta T equivalent, that is TB times delta T divided by TB plus delta T. So this is your T delta T as it is, as I said, and here is your pressure. See, so we got this one, and we're gonna go with logarithmic scale. See, guys. So this is what we have. This is Horner MDH, and this is your first infinite Acton line, and this is your second infinite Acton line. Let me make them clear. Not like this too much. Let me put the titles. This is DT hours. Okay. And this is BWS PSI. You could use also delta V. You could use also delta V. Okay, and let me change the grid lines, make them black. For this one also black. And now I am going to add the minor grid lines. I am going to change them also. Make them light blue here also. Okay, and this is your markers. Let me make them bigger also. So here's what you have. Now, apparently that we could have also two infinite action line. This is your first infinite action line. See, this is your first infinite action line. And this is your second infinite action line. This is your second infinite action line. Okay. Now I'm going to calculate M1, and let me see how much M1. Okay. So M1, this is 100. So 335, 3350, 60, 3375, 3375 minus 331, same 3315. So this is 60. Let me see M2. M2. Let me change a little bit in M2. So see, this should be like this. So now for M2, let me do it like this. Make it here. Okay, good now. We are good. Okay. So M2, this would be 3400 minus 328. 328. See, 120. So we are good. Now I am going to calculate the permeability skin factor for this case using Miller-Dice-Hutchinson, and the mathematical models in this case will be, let me bring them in front of you. This is for Miller-Dice-Hutchinson, corner. So the permeability is going to be the same, except D. D will be calculated by this model. So for Miller-Dice, this is for D, okay? While the permeability and the skin factor, they will be the same. So permeability and skin factor will be the same. Let me do it again. So this would be good. Times Q mu oil formation volume factor divided by slope. Be careful, the first infinite action line formation thickness. So this is your permeability millidarcy. Now skin factor you need for dt 1 hour. See, 1 hour, and then you have to calculate BWS 1 hour. This would be taken from the flow directly. So 1 hour, here is 1 hour. See guys, this is 1 hour. You're gonna move where? You're gonna move to the first infinite action line. So this is your first infinite action line. See guys, and you will read the pressure, that is 3250 psi, and you will be able to calculate skin factor, that is 1.151 times what? times delta B. What is delta B? The pressure for 1 hour minus the, the pressure at the moment of the shut-in. Where is that? This one. Divided by the slope of the first infinite actor line minus log K. This is K. Divided by what? Divided by phi mu CT, phi mu CT RW square, okay, plus 3.23, and this is your skin factor. Why? This should be here. Okay, so this is your skin factor. Now, Tx taken from delta T directly. Where is your Tx? So this is your Tx, see guys? This is your Tx. It is almost 40, 10, 20, 30, 40. So D in this case will be what? Will be 0.01217 times square root of what? Square root of K delta K delta Tx. This is delta Tx, see? Divided by phi mu Ct, phi mu Ct, phi mu and Ct. This is Ct. So close, close, and this is your distance. So fit. Okay. So here is the solution for the distance to the reservoir boundary or the distance to the fault. If we have a fault, using Horner plot, using Miller-Dietrich-Hutchinson. And before that, we have solved the one for pressure drawdown test. So let me save this one to you, and then I'm going to post both of them, 161, 162, using the Telegram. Now let me get back to what I have. This is 162. Here is, and for the pressure derivative, yes, we could, but it is not important, so we're not going to go with this one. Now I'm going to stop at this point. We will start with average reservoir pressure next week. So next week, I'm going to start talking about how to calculate average reservoir pressure from the pressure build-up test. We have talked about the protocols, the procedures to calculate average reservoir pressure using Horner plot. But we do have another techniques to calculate average reservoir pressure, not only by Horner plot. For example, from Miller-Dietrich-Hutchinson, we don't know how to get initial reservoir pressure or average reservoir pressure. No, we do have another technique given by Miller-Dietrich-Hutchinson to calculate average reservoir pressure, and we are going to cover this topic next week. Okay, guys? Thank you so much.